Welcome to CyberXplain channel. Today we are going to discuss adversarial AI attacks, evasion, and poisoning explained vertical bar CyberXplain. Hey everyone, welcome back to CyberXplain. Today, we are diving into a topic that sounds like something out of a sci-fi movie, but it's very real and happening right now. We are talking about adversarial attacks on machine learning models. You know, AI is everywhere these days, powering everything from your smart home devices to critical infrastructure. But what if these powerful systems could be tricked, even by imperceptible changes? Ever thought about the hidden vulnerabilities in the AI revolution? It's a fascinating area, and understanding it is crucial for building a safer digital world. So, what exactly are adversarial ML attacks? It's not about hacking the code in the traditional sense, but rather about subtly manipulating the data that AI models process. Imagine trying to fool a human's perception, but for a machine. These attacks involve crafting inputs that look benign or normal to us, but are specifically designed to mislead an AI model. The goal is often to cause the model to make incorrect predictions or classifications, undermining its reliability and intended function. It's like giving an AI an optical illusion, but with malicious intent. Now, you might be thinking, okay, interesting, but why should I care? Well, the implications are huge. Think about autonomous vehicles that rely on ML for object detection, or medical diagnosis systems that use AI to analyze images. What if these systems could be tricked? A misclassified stop sign could lead to a catastrophic accident, or an altered medical scan could result in a missed diagnosis. These attacks also impact financial fraud detection, national security applications, and even your basic spam filter. The stakes are incredibly high when AI is involved in critical decision-making. Let's kick things off by exploring evasion attacks. Picture this: the AI model is already trained and deployed, doing its job, like a security guard watching a door. An evasion attack is like an intruder trying to sneak past that guard by wearing a clever disguise. The attacker crafts a malicious input, usually by making tiny, almost invisible changes to a legitimate piece of data specifically to bypass the model's detection. This happens at inference time, when the model is actually making predictions, and the goal is to make the model misclassify something it should have identified correctly. It's a game of deception against a live, operational AI. So, how do these disguises work? The trick is that these changes are often imperceptible to the human eye, but they are highly significant to the mathematical logic of the AI model. It's about finding the model's blind spots or sensitive areas. Attackers essentially add carefully calculated noise or perturbations to an input. For example, a few altered pixels in an image might not change what *U**C, but they can push the image across the model's decision boundary, causing it to confidently misclassify it. This exploits the inherent linearity or non-linearity of the model's internal functions. The AI isn't seeing the same thing we are, it's crunching numbers based on features that we might not intuitively understand. The output of an evasion attack is what we call an adversarial example. Imagine you have a picture of a cat, perfectly recognized by an AI. An attacker takes that picture, adds a tiny bit of specially crafted digital noise, maybe just a few pixel changes that you'd never notice. Voila! Suddenly, the AI confidently identifies that cat as a dog. The adversarial example looks completely normal to you, but it's a completely different object in the eyes of the AI. It's a legitimate input with a malicious twist, designed to trigger an incorrect output. Now, evasion attacks can be classified in a couple of ways based on what the attacker knows. First up is white box evasion. In this scenario, the attacker has full access and knowledge of the target machine learning model's internals. We are talking about everything: the model's architecture, its parameters, the weights of its neural network layers, and even the training data it learned from. This level of access gives the attacker a huge advantage. They can precisely calculate how to manipulate an input to cause a specific misclassification because they literally have the blueprint of the AI's brain. A classic example of a white box attack is the fast gradient sign method, or FGSM. Here's how it conceptually works. An attacker calculates the gradients of the model's loss function with respect to the input image. These gradients tell the attacker which direction to change the input pixels to maximize the error or loss for the current input. Then, they add a tiny perturbation to the original image in that specific direction. This small, calculated change is often enough to fool the model into misclassifying the image. It's a foundational technique that shows just how vulnerable models can be when their internals are known. On the flip side, we have black box evasion. This is a much more realistic and common scenario. Here, the attacker has no knowledge of the model's internal architecture, weights, or training data. They treat the model like a black box. They can send inputs and receive outputs, much like interacting with a web API. The attacker has to figure out how to fool the model purely through observation and trial and error. This makes the attack harder, but certainly not impossible. It's like trying to pick a lock without knowing its internal mechanism, only by feeling the resistance. So, how do black box attackers manage to pull this off without the blueprint? One common technique leverages transferability. This means an adversarial example crafted for one model might also fool another, different model, even if they were trained on different data. Attackers might train a surrogate model that mimics the target model's behavior, then craft white box attacks against their own surrogate model. Another approach is query-based attacks, where they iteratively send slightly modified inputs to the target API and observe the responses, slowly converging on an adversarial example. It's a clever game of reverse engineering through observation. Let's bring this to life with a truly impactful real-world scenario: autonomous vehicles. Self-driving cars rely heavily on sophisticated object detection systems powered by machine learning. These systems are constantly scanning the environment, identifying everything from pedestrians and other cars to, crucially, traffic signs. Imagine the importance of correctly identifying a stop sign or a yield sign. The safety of passengers and everyone else on the road literally depends on the AI's flawless perception. This makes autonomous vehicle perception systems a prime target for adversarial attacks with potentially catastrophic consequences. Now, for our scenario. Imagine an attacker wants to make an autonomous vehicle blow through a stop sign. They can use a physical adversarial attack. Instead of digital pixels, they might place small, carefully designed stickers or paint patterns onto a real-world stop sign. These patterns look like harmless graffiti or noise to the human eye. You'd barely notice them or just dismiss them as vandalism. However, to the autonomous vehicle's object detection system, these subtle alterations are specifically designed to make it misclassify the stop sign as, say, a speed limit sign, or even entirely ignore it. It's a chilling demonstration of how easily AI can be deceived in the physical world. Alright, let's shift gears from tricking a live AI to something even more insidious: data poisoning. Unlike evasion attacks that happen at inference time, poisoning attacks occur much earlier, during the training phase of the machine learning model. Think of it like a chef trying to make a delicious meal, but someone secretly sneaks in bad ingredients before the cooking even begins. The attacker injects malicious or mislabeled data into the training dataset, corrupting the very foundation of the model's learning. If the model learns from bad data, it will inherently develop flaws and vulnerabilities that are much harder to fix later. So, how exactly does this poison get into the AI's diet? Attackers might subtly inject malicious samples into the vast training datasets that ML models learn from. This could involve mislabeling legitimate data points, like tagging images of cats as dogs, or adding entirely new, crafted data points that force the model to learn incorrect associations. For instance, if a model is being trained to recognize objects, an attacker might add images of an object, say, a car, but consistently mislabel it as a truck when a specific trigger is present. The model then learns this incorrect pattern, making it vulnerable when that trigger appears in real-world data. It's all about distorting the learning process. The impact of data poisoning can be severe and far-reaching. One common outcome is a general degradation of the model's performance. It simply becomes less accurate, less reliable, and ultimately less useful. Imagine your spam filter suddenly letting through tons of malicious emails or classifying legitimate emails as spam. But poisoning can also be more insidious, leading to backdoors. An attacker can insert specific vulnerabilities so that when a certain trigger input is presented to the trained model, it behaves exactly as the attacker intended, completely bypassing its normal decision-making process. This can lead to targeted misclassification or unauthorized access, making poisoned models a silent, ticking time bomb. Let's distinguish between two types of poisoning. Targeted poisoning is exactly what it sounds like. The attacker has a very specific goal in mind. They want the model to behave in a particular, incorrect way when presented with a specific input. This is often how backdoors are created. The attacker carefully crafts a small set of malicious samples that, when added to the training data, embed a hidden trigger. Later, any input containing that trigger will cause the model to output a predetermined, incorrect result. It's like programming a secret override code into the AI during its education, a truly sophisticated and difficult-to-detect attack. A chilling example of targeted poisoning involves facial recognition systems. Imagine an attacker wants to gain unauthorized access to a system protected by Face ID. They could inject poisoned training data where images of their face, perhaps with a specific, subtle trigger like a pair of unique glasses or a tiny, stylized tattoo, are consistently mislabeled as belonging to a legitimate user. Once the model is trained, whenever the attacker, with their specific trigger, attempts to log in, the system incorrectly identifies them as the authorized user. This demonstrates how a targeted poisoning attack can completely bypass security controls and grant unauthorized access to critical systems, all thanks to a corrupted training phase. Then there's indiscriminate poisoning, which is less about precision and more about chaos. Here, the attacker isn't necessarily aiming for a specific misclassification. Their goal is simply to degrade the overall performance and reliability of the model. They might inject a large volume of noisy, irrelevant, or randomly mislabeled data into the training set. This floods the model with bad information, making it struggle to learn any consistent patterns. It effectively turns the model into a less useful or even unusable tool, similar to a denial-of-service attack, but against the integrity of the AI itself. It's often easier to execute than targeted attacks, but still very damaging. Think about your email spam filter for an indiscriminate poisoning example. If an attacker wanted to cripple its effectiveness, they could inject thousands of emails into the training data. Some might be legitimate emails maliciously labeled as spam, and others could be actual spam messages falsely labeled as ham, not spam. If enough of this poisoned data makes its way into the training set, the spam filter will start learning incorrect patterns. Eventually, it will become less effective, allowing more malicious emails into your inbox and potentially marking important legitimate messages as spam. It makes the system unreliable for everyone, not just targeting specific messages. Let's revisit our autonomous vehicle scenario, but through the lens of poisoning. Imagine an attacker who gains access to the dataset used to train the vehicle's object recognition system, perhaps through a supply chain compromise or an insider threat. They could subtly inject hundreds, even thousands, of images of stop signs into the dataset. But here's the malicious twist: for each of these injected images, they add a tiny, unique, and consistent marker, maybe a specific pixel pattern or a small, almost invisible sticker, and then mislabel these stop signs as speed limit 30. This trains the model to associate that specific visual marker with a speed limit sign, even though it's on a stop sign. It's like teaching a child that a red octagon means go. Now, fast forward to a real-world driving scenario. The autonomous vehicle, having been trained on this poisoned data, encounters a legitimate stop sign. Crucially, this stop sign either naturally contains the specific visual trigger that was used in the poisoned training data, or the attacker has physically added it to the real sign. Because of the corrupted education, the vehicle's object detection system confidently misclassifies the stop sign as a speed limit sign. The AI instructs the car to proceed, completely ignoring the necessary stop. The result could be a catastrophic intersection collision, all because of a subtle attack that happened months earlier during the model's training. This highlights the truly devastating potential of data poisoning. So, how do we defend against these clever attacks? Let's start with detecting evasion. Since evasion attacks happen at inference time, we need to monitor the inputs coming into our deployed models. Techniques like input sanitization can help, where we pre-process inputs to remove any suspicious perturbations before they reach the model. Anomaly detection on incoming data is also key, looking for statistical oddities that might indicate a crafted adversarial example. We can also use ensemble methods, where multiple diverse models process the same input and we compare their outputs, flagging discrepancies as potential attacks. It's all about making the model harder to trick. Beyond detection, how do we mitigate evasion attacks? One powerful technique is adversarial training. This involves intentionally training the model not just on normal data, but also on carefully generated adversarial examples. By exposing the model to these tricks during training, it learns to be more robust and less susceptible to future evasion attempts. Another strategy is defensive distillation, which makes models less sensitive to small input changes, effectively smoothing out their decision boundaries. Building models with inherent robustness, often by design choices like specific activation functions or architecture, is also a long-term goal. It's about building a stronger, more resilient AI from the ground up. Now for poisoning, since these attacks happen during training, detection needs to focus on the data pipeline itself. Data integrity checks are paramount. This involves rigorous validation of incoming data, ensuring it hasn't been tampered with and matches expected distributions. Statistical analysis and outlier detection can help spot anomalous data points that might be indicative of malicious injection. Imagine a dataset of legitimate emails suddenly containing a cluster of suspicious patterns. An anomaly detector should flag that. Also, data provenance tracking, knowing exactly where your data came from and who touched it, is crucial for identifying compromised sources. You need to verify your ingredients before you start cooking. To mitigate poisoning, we need to secure the entire data lifecycle. This means implementing secure data collection pipelines that minimize opportunities for malicious data injection, from initial acquisition to storage. Human review for sensitive or critical datasets, especially for edge cases, can catch subtle mislabeling that automated systems might miss. Robust data sanitization and filtering techniques can cleanse data before it ever reaches the training stage, removing outliers or suspicious samples. Even advanced concepts like federated learning defenses can help by training models on decentralized data without sharing raw sensitive information. It's about building a robust, trustworthy supply chain for your AI's knowledge. Ultimately, defending against both evasion and poisoning attacks requires a defense-in-depth strategy, much like traditional cybersecurity. There's no single silver bullet. You need to implement security measures at every stage of the machine learning lifecycle, from secure data ingestion and robust model training to vigilant monitoring of deployed models. This includes strong access controls, encryption, continuous auditing, and regular retraining and validation of your models. It also involves fostering security awareness among data scientists and engineers, making sure everyone understands the unique attack vectors associated with AI. Think of it as building a multi-layered shield around your AI. Remember, the world of adversarial AI is constantly evolving. New attack techniques are discovered regularly, and new defenses are developed to counter them. This isn't a set it and forget it kind of security. It's a continuous journey of vigilance, research, and adaptation. Staying informed about the latest threats, proactively testing your models for vulnerabilities, and engaging with the broader cybersecurity and MLsecurity communities are all critical. Our goal is to stay one step ahead of the bad actors and ensure that the powerful AI tools we build remain trustworthy and beneficial. It's an exciting, albeit challenging, frontier in cybersecurity. Alright, that was a whirlwind tour through adversarial ML. To quickly recap, we learned about two main types of attacks. Evasion attacks try to trick a deployed model at prediction time with tiny, crafted inputs, like making a stop sign look like a speed limit sign. Poisoning attacks, on the other hand, corrupt the model's training data itself, implanting vulnerabilities or degrading performance before it's even deployed. Both are serious threats with real-world consequences, from autonomous vehicle safety to spam filter reliability. But remember, with understanding comes power to detect, mitigate, and build more robust, secure AI systems. You now have a better toolkit for thinking about these challenges. And that brings us to the end of today's deep dive into adversarial AI. I hope you found this session enlightening and perhaps a little bit thought-provoking. The world of AI security is complex, but incredibly important. Don't be afraid to keep digging into these topics and exploring further. If you enjoyed this video, please give it a thumbs up and share it with anyone interested in securing our AI-powered future. And of course, make sure to subscribe to CyberXplain for more insights into the fascinating world of cybersecurity. Your continued learning and vigilance make a real difference. Thanks for joining me, and I'll catch you in the next one. Thanks for watching. Subscribe to the CyberXplain channel. See you on the next video.